Good morning. I'm going to talk about rules engines. This is some of the stuff, some pretty cool stuff we're doing at the moment with the Pivotal guys, obviously with VMware and EMC before, which is now Pivotal. This is part of this we put into production, or a chunk of this we put into production. A lot of it is stuff that's going into clients. I think you'll find it's quite leading edge, so please feel free to ask questions during. Obviously, hopefully, we'll have plenty of time towards the end for questions. But if you have a question halfway through, please feel free to interrupt me, perhaps just to provide some more context, etc. A little bit about me. Some of you know me. I'm a CTO, so I've been doing the programming many years ago. I did lots of assembler, I did C, C++, a lot of Java when it came out, right from the early days. I still program a lot, so I sit on planes. I spend my life flying around the world. So most of my most efficient programming time is when I sit on the plane, get the laptop out, and shut off from everyone else, the phone calls and the tweets, the Twitters, all those sorts of bits and pieces. But a lot of the stuff I do, I don't go into the nitty-gritty detail. Fortunately, I have a team of people that do that. So some of the questions, if you're going to get into the details of an implementation or part of the Spring, the sort of stuff that I'd say, someone else does that, they do the details and bits. So I cover the layer above that. But I'm certainly deep into technology. I'm going to, most of you all know these sort of buzzwords, so we're going to look at CEP, big data and things, so I'm going to give you my definitions of these. I tend to find them used a lot by vendors and things, so I'll give you sort of the definition that I use on these, and hopefully that'll provide some context for sort of how it fits in. What I'm going to do on the agenda, I'm going to look at different types of rules. So again, I want to be clear about when we talk about rules engines, there's lots of different types of rules, and some people, and I find this a lot, particularly when we're having discussions both internally or with clients, we say, oh, we'll put a rules engine in that, or although that's just rules, or CEP, people have different concepts of what the types, what do we mean by these rules. So I want to sort of go through a little bit of clarity about the different types of rules that we have. And there's obviously a massive amount of overlap, and a lot of the technologies that do these overlap in a huge way. So sometimes when you look at conceptually, I can do some rules in this bit, it'll also sort of move over to the other side as well. So again, I'm going to go through that with a bit of clarity. We're not going to go big into big data. It's just a couple of slides, but it's the sort of stuff that we're doing. Some of the reasons that we're going to the high performance here is because we're looking at some really seriously high performance and very large numbers, and that's definitely big data, and that's the realm of the EMC sort of side of things. So I need to cover that and at least give you the definitions behind that. We're looking at parsing messages in around the sort of million per second. That's the sort of figures that we need to achieve on this. So again, I'm going to show you how we achieve that and some of the procedures we went from, both parsing the messages, handling the messages, putting them in through Spring, through the sort of spell expressions, and then how we're passing those on into the memory side, into Gemfire and big data. And in-memory compilation, which is obviously some of the secrets that we're using, and then sort of how we put all this together. So let's get going. So on the rules side of things, there's lots of different types. We can take a message, a simple part of a message, and say that there's a rule in this, that this date must be greater than that date, that we start with those sorts of those sort of rules. We can get further into the rules and say, if this sort of message arrives, I want it to do this, and we can get right the way down to if this message has a particular value which is greater than the average of all of the values that arrived over the last 5 minutes, etc., where we've got moving averages, then trigger these sorts of events. So I've put these down into about 5 different types of rules. So we got what I call message syntax and semantics. Let me describe the difference between those. I'll go into more detail of each of these. The syntax is basically the date format, for example. This is an integer, it's in hex format, or it's in binary format. So the semantics are more the business rules. It's the sort of things that the business say that, as I said before, this date must be a weekday, for example, or this amount must be smaller than this amount, or it must be less than 2% of another amount. So these are the semantic business rules. And these often get mixed up because Some of the syntactic rules are required at the network level when we're parsing things. If we need to understand a date, the trader, the dealer, the person using the date doesn't really care what the format is that it's put down, but the computer programming language we're using obviously has to be able to parse and understand the date when it reads it. So there's a sort of an overlap between these. Then we've got routing and decision rules. So we've parsed the message, we've managed the syntax, and we need to be able to push these through a system. We need to be able to decide these sorts of messages go this way, these messages go the other way. Then we've got rules engines. This is where it's a little bit more complex than simply deciding which way to go in something. This is where there's an overlap between a rules engine and CEP. And I find this, from my point of view, a little bit difficult to say this is a rules engine and this is not CEP or this is CEP. So I find there's a big overlap between these. And a lot of vendors will try and distinguish their CEP engine as being specifically CEP because it differentiates itself from a rules engine in a specific way. But I find that boundary a little bit flaky. And then finally, an interesting one that my colleagues reminded me of is matching engines and transformation rules. And as I say, we'll go into these in a little bit more detail. So the syntactic rules are extremely important when we're parsing the messages. If, for example, where the US put the date format the wrong way round, so you put the month before the date, it's very important that we obviously get 9/11, for example, or whatever it is, 12, what do you call it today? It's 9/12 or something. When people say, oh, we're going to go for delivery on 9/15, I'm thinking, that's a little early in the morning. What they mean here is obviously the 15th of September, which completely confuses me. But it's very important that we get these rules, and we have to apply these rules while we're parsing. And this is one of the things that can be quite time-consuming while parsing the messages. But it's vital, obviously, to get the dates right. It's vital to get in this particular case, we got A to Z, as you'd call it, 3 characters. This would be like a currency. It's vital that we sort of parse these messages. So they're very important to the meaning of the message that we're parsing. And we can have some stuff which is not particularly part of the message. So we can have checksums, CRCs. Often we have fields that say, here's the number of bytes that are following, for example. The semantic rules are a little bit more detailed. If we could have a currency, so for example, the first one there, we've got uppercase 3 characters. That's the syntax. But if you put XXX, it conforms to the syntax but not the semantics. XXX is not a currency. So we need to provide a little bit more context. You could then go to say, yes, it's a currency, but if you were trading, for example, in Eurozone, there's a difference between the Euro and the Eurozone. The Eurozone includes a lot more countries. So we'd need to further restrict that list into the semantics about what we're actually dealing with in this particular case. So there's a difference between semantics and syntax. Then we get onto the routing, and this is where the realms of Spring integration, Spring batch, and other products in this area, the mules, the camels, the fuse, etc., where you start to get into the realms of the ESBs. So we've now parsed the message, we've conformed to all of the rules behind that. We now want to be able to say, if this is in this particular group, this particular currency, we want to pass this onto this direction, onto that direction. This is what we're going to be looking at a little bit later in a little bit more detail. Why? Because it's particularly important. You're going to make the assumption that you're parsing all of the messages because you can't make any decisions about the messages until you've actually parsed them. So it's taken for granted that you're going to parse all of these things. You need to understand the content. But now, in order to be able to route them, you've now got to take the information out of the message and pass that in for the ability to apply, for example, one of these spell queries into it. And this, if we can't start to do triage or start to sort the messages at this point, if you've got 100,000 messages arriving a second, you've got to deal with those at that sort of speed. One of the advantages of being able to actually parse them at this level is you can say, all of certain messages go one way, other messages go another way, other messages go another way, and then you've now got 3 different areas which have now roughly 1/3 or a smaller amount, and you've got more distributed processing to cope with them. So this is a particularly important part of the rules. The rules engine is again the bit where I said there's a sort of delicate, more sort of vendor attributed balance between what is a rule engine and what is CEP. So I'm going to leave that boundary as sort of undefined. Something to me is, if it's a powerful rules engine, it's going to be fairly capable of doing CEP. Where CEP tends to fit, and if I move on to the next slide, it's where you find typically quant traders and people saying, if the value of this share over a particular period of time, over a 15-minute moving average, exceeds or goes up generally, or there's a general trend and another share goes down, then buy this one and sell this one as long as I have these to sell, etc., etc. So that's where the term complex comes from, because the rules are increasingly complex. One of the challenges we have, if you think back to the message level, the messages are typically put into a specific format because it's easy for the computer to process. So go back 30 years, 20 years, and even today still we've got binary messages. So things are put into binary because it's obviously easier for the computer to deal with, but that's not what the people who create the rules and sit at this level, at the CEP level, want to deal with things. They want to deal with things in a semantic concept. That's my currency, that's my buy amount, that's my sell amount, that's the date, that's the time. They don't want to take a time to be, as we would call it, oh, it's a Unix epoch. So it's the date since, there's a number of seconds since 1970, for example. There's a difference. And one of the challenges we have here is when we're providing a GUI or something for users to use at this level, at a rules engine or CEP, we have to abstract the syntax and the wire level syntax, the details of how the message is put onto the wire, into a business context, and that's one of the challenges we have. If we provide this with Java, for example, the guy who's defining these rules is typically used to an Excel spreadsheet, so they find it very difficult to get the brackets, the syntax, why does this method return, why can't I cast this byte array into a string, for example. They don't want to deal with these language problems. So we're finding increasing use of things like Scala, which allow us to provide some sort of abstraction of the details of the language at this point. Finally, in the rules, the matching and transformation, as I say, there was a colleague who reminded me on this. This is a sort of a special case of rules. If we had a large collection of, again, I apologize for going back into trading all the time because my sort of world revolves around financial services, but you imagine there's a big pile of trades, deals, buy this, sell that, etc. What you've got to do is to look for pairs. So if two banks, one is selling something, the other one's buying something, they exchange the details afterwards, and you need to make sure that what the other bank bought is precisely what you sold for the same value. And they compare these two, and that's called matching. And at the end of the day, what happens is that they say, here's a list of all the things I bought and sold, and that's called reconciliation. So it's the same as you would do with your Visa bills at in the months when you get them. For those that bother, you can go through all the list of things that you bought and sold and the receipts you've got. That's reconciling the account. And this happens hundreds and hundreds of times with every trade as it goes through the system. So this is a different type of matching, but what we're doing here is we're saying for the trade or for the message, check that this is the same, check that this is the same, and we're doing this for every single detail through the message, with the exception of some fields where we say check this is almost the same as this. So occasionally you may find, obviously the timestamp is going to be different because even though they're synchronized, there's the time to transform the message. So this must be within a second of this one, for example, or the amounts, people add commission and they add things, so make sure that this amount is within equivalent of $50 of the other amount. So there's some interesting matching and rules engines that can be provided in that. So now we've got multiple layers of rules. So the messages are coming in, we need to do the syntax, we need the semantics of the rules, we need to do the routing of the rules, and as you move up through the layers, eventually what we've got is an abstracted message, which is now abstracted from the message or the wire level, and is now in a more business context, and we now need to provide this message far more business-like into a rules engine or a CEP engine for a user to use who's, again, typically used to an Excel spreadsheet. So there's a big difference from going from the binary at the bottom right the way up through to the sort of Excel spreadsheet people. Distributed rules. So where does this come in? Well, if you've got a small selection of messages where we're getting 500, 1,000 a second or something, or even less, you're processing a batch, it's very easy to do that on a single machine and push them in. But when you start to get to the realms of 20, 50, 100,000 messages a second constantly in a trading floor, 8 hours, 12 hours a day as they come around the clock from various different feeds, or in a telco environment where you've got literally 24 by 7, 7 days a week, 365 days a year, it does not stop. These messages come in constantly. There's no way you're going to treat these on a single machine. So what we're trying to do here is have, it's sort of like if you imagine a sphere, excuse me, on the outside, we've got lots of different messages coming in, and in the middle you've got the classic database, big data, or you've got to store these somewhere because that's what you're going to be trawling through at the end of the day to do your Hadoop map reduce on it, to trawl through looking for trends, looking for, in the case of credit cards, you're looking for fraud and all these sort of things. So it's got to come into the center. So what you're trying to do is to process these at the syntactic and semantic layer on the outside and basically filter out as much of the crap as you can before you finally store the gems in the middle. So a lot of these are distributed. My definition of big data, as sort of people ask, is something that won't fit on one machine. That's sort of the easiest way that I can define it. If you can fit something on one machine, it's a database, or you can put it into a database. If you can process it on one machine, it's not big data. A lot of the things you can argue, yes, you can process through 1 million, you can process through 1 billion on an average laptop these days, but 1 billion we can get in less than an hour and these sort of things. So we're looking at, again, 100,000 messages a second, 24 by 7, that's 8.6 billion a day, and that's typically an average, and that's not just 5 days a week, that's every day. And you've got to put those in, store them, and trawl through them, and provide some statistics out of this. If you even look at the size, we're not storing massive messages here. These are 500 bytes. They're pretty small, but this pretty quickly amounts up, as you can see here. After 6 months, we're into 1.5 petabytes. You don't necessarily want to zip these or tar them either, because at that sort of volume, there's an awful lot of processing to do to untar them or to uncompress them. So there's a lot of processing. That is big data, and that's if you've got to do a sort, a search, a query or something on this, you've got to distribute that up because even the indices that come out of this sort of data is too big to fit on one machine. So that's, for me, is the definition of where sort of big data separates out from the single machine. And the architecture in these, this to me is nothing new. This is the sort of stuff where we've had these realms of data for 10, 20 years. It's always been bigger than we can manage because it's just it's almost like the Moore's law. The bigger the computers get, people always push the edge of it, and you get more and more data because you're collecting the data from, in fact, in globalization, it just gets bigger and bigger and bigger because you connect to more people, to more industries, and you just collect more and more data. So this, by definition, is extremely distributed. This is a realm where we're constantly working in a distributed environment. There's nothing that sits and works on one machine on single threads. We're working on multiple threads, multiple machines, in a very, very distributed, networked situation or environment. So getting down to it, I'm going to come up, I've got 2 scenarios here. I'm going to concentrate on the telco scenario here because it's the one that I've had my head stuck in for the last month or so. And it was the easiest one that I could cut and paste examples out of, and so we'll get into a little bit of code shortly. So the telcos, what are they doing? Well, every time you turn your phone, and even when you're walking around, your phone is communicating with a cell tower. Now, it's not necessarily a cell tower that's sitting outside on the side of the freeway. A lot of shopping malls have these little pico cells in them. So as you walk into the shopping mall, your phone will switch across to the pico cells. People now have them in their houses. If you can't get a signal, you can buy one of these things, plug them into the the Wi-Fi that you've got, and it becomes a small in-house cell tower. So we've got these. We've got the ones that are sitting in shopping malls. We've got the ones sitting in little shadow areas. The telcos find that there are little shadows created by buildings, so they put a little tiny tower, or not a tower, but a small thing that just covers that one area. Then you've got the larger towers. So your phone is switching across to all of these. So if you've got a call, the only one that it doesn't seem to work with, in my experience, is AT&T, because they drop the calls constantly. But in most other countries, when you're actually walking around, it doesn't actually drop the call. And what happens is it negotiates, it knows where the next towers are, and it can actually move your call onto the next tower. The same with the sessionless data session that you've got. If you're downloading something, that continues to go on to the cell towers. So what they're looking to do, there's a number of initiatives, certainly in the European Union, and I'm sure it's the same here, that if a phone is stolen, those phones have got to be switched off. If there's some unfortunate action, shall we say terrorism or something like that, they've got to track those phones. There are laws in Europe about being able to access the data of those in about 30 seconds. Every telco has to provide that information, and so of course that drives them to produce this. You've got consumers wanting, or perhaps not wanting, but being persuaded to opt in for offers. So as you walk near a particular shopping mall, for example, you get an offer to say something is on discount. They know you're there because they can see exactly where you are with all of the GPS data or just basically triangulation on the cell towers. So there's all this information. If you're downloading, when I travel into London in the mornings, everyone's sitting there watching TV on their phones. And they're getting this streamed through the data. They're all sitting there watching either films that have stored on their phones, or they're watching live TV, catching up on the news. This data is streamed from the towers. If you can actually predict what information or what data these people are getting from the next cell tower, you can start to cache some of this stuff, and the network providers can save some money. So there's a lot of information which they're mandated to provide, and there's also information where they can save money on this, and there's also information that they can start to sell to us, the consumer. So that's the drive behind this. Where does the money come from? Well, Vodafone, for example, just as an example, just sold their looking to sell their 45% stake in Verizon, $130 billion. So it's a nice bit of cash that they got to play with this, and it would be great to know that that's now gone into the realms of the likes of us to program in if we can get those sorts of deals. So there's plenty of money in the telcos. And the investment banks, they're basically looking for all of the trades. They need to trawl through these and look for what-if scenarios. If I had sold this, if I had bought this, or if I had this particular rule, how much money could I have made? And obviously that's the sort of realms we're looking at. So getting down to it, what's really important here is we absolutely must meet the volumes of this. So when I say 100,000 a second, we've got the trades coming in averaging maybe 50 to 100,000 a second, but imagine you get, well, you can understand you get peaks from this. What would happen if you can't manage these peaks? So imagine if you look at the volume over a 24-hour period, you're going to, obviously you can average this out. Let's just make it a nice round number of 100,000 a second. Quiet times of the day, it's going to go down to maybe 20,000, even 10,000. But when it gets really busy, like in the morning for a telco and then trading, just as figures are released, maybe at 1 o'clock as the Fed released the latest employment or unemployment figures, there's a massive amount of trading that goes through, and you have to be able to cope with these peaks. Put it into perspective. Again, looking at a telco example, if you can process 200,000 a second, and you get a peak of 400,000 a second, which lasts for an hour. Let's say Thanksgiving, people sending best wishes, or there's some major event that happens, an unfortunate accident or something. Of course, everybody's tweeting and calling. There's a massive amount of volume that goes through this. If you can process 200,000 a second, and you have 1 hour at 400,000 a second, and then the volume goes down afterwards, it's going to take you 4 hours to catch up. Not just that, but you need 360 gigabytes of RAM to queue it. Remembering that you've also got mandatory requirements to find where certain phones are for unfortunate terrorist, types of things within 30 seconds. So you've immediately out of compliance. So there's no way that you can say, fine, we'll manage the average or we'll double the average. You have to manage the peaks as well. And the peaks you never know because they just go up. In the trading environments at the Chicago Mercantile Exchange, it averages, typically we can hit 100,000 or so, but in the last few years it's hit 380,000 messages a second just in one exchange. That's a lot of volume, and you don't want to be not processing those messages at that peak, because that's exactly when you want to be processing the messages to get them coming through, because that's the time when you make your money. So it's the time you've really got to hit them. So what I'm going to go into now, and looking at the programming side of this, is our drive to try and hit these peaks. And we don't know what these peaks are, so we're sort of guessing in a lot of cases. So we know what the averages are. We can sort of ask people, say, okay, the average is, let's say, 100,000, again, picking a round number. We think the peak's around 400,000. But again, just look at the numbers here. If they say it's 400,000, but it turns out to be 800,000, we're going to be in trouble. So we've got to be a long way ahead of this. So messages coming in, first thing we've got to do is parse them. So what we've done, we've used Java binding technology. It's from my own company, so I'll just put that straight in. It's a company called C24. Basically, it's built on Castor. It basically does binding from as Castor, JAXB, JIBEX, all these things do. It binds from XML, but we've extended that now to do binary, comma delimited files, and some of these other things. So what happens if you were parsing XML? So I'll bring this into the sort of realms that everyone understands easily. If you're parsing XML, you've got two options. You can use a SAX parser or a DOM parser, or the DOM uses the SAX parser. But what happens is you can either process all of the information and bung it into a DOM, a document object model, and if you need to access it, it's immediately available and really quick. But if you don't need all of the information, you've parsed the entire message, created a hell of a lot of objects for no reason at all. Particularly if you've got 40 objects or 40 elements in the XML and you only need 3 of them, you've done a lot of extra parsing and you've created 40 elements. Now at 1 million a second, that's 40 million elements or objects that you've created, in addition to all of the little temporary strings and things that you've created on the fly. That's a lot of garbage collection that kicks in. So this is one of the first things that we found was, if you're parsing these things and you're putting the information, what we did was to create the equivalent of a document object model. So we parsed the data, put it into these things. It works pretty well. So we parse the stuff straight through. It would do 20,000 a second per core. For most cases, that's adequate. But when you want to hit 1 million, it's far from adequate. These are the sorts of specs we had. This is an open standard RFC 2865. It's the radius, what they call the radius standard. It's one of zillions of different standards. Interestingly, the next standard after this, because this is pretty old, is called diameter, which I thought was quite clever because it's just twice the radius, naturally. Whether it actually stands for something, I don't know, but I just thought it was a rather clever little renaming here. There are 77 pages of this sort of stuff. Most of you that have been slightly older than in your 20s or something, you'll remember binary bits and things. The weird thing is, every standard you look at, it's slightly different. One of the standards numbers the bits from 1 to 8. That to me is rather strange, but they do it. Another standard, like this one, numbers the bits from 0 to 7. You'll notice this one, for me, is the wrong way around, because I often see bit 0 here and 32 or 31 on the other side. But each one of these standards is slightly different. So somebody's got to come in and manually convert that spec into a Java object. And that's pretty time-consuming and pretty heavy. And if we were to take this out, we look at these, we've got type, length, vendor types, all these different bits and pieces. If we take these out and put them into objects, again, we're doing what I've just said is rather expensive. We're creating lots and lots of objects as we pass this through. So we've got to be pretty careful as we go through this. Looking at part of the fixed spec, this is from financial services. Again, back into the bytes and bits, all sorts of little tiny gems hidden in there to say if this bit's set, then this field doesn't exist. If these 4 bits here represent the number between 1 and or 0 and 7, for example, there's lots of little sort of weird gems hidden in here to sort of confuse you. What we've done is basically take these models and we've modeled these into our tool here. Again, this is exactly like gem-cac-gs, JAX-B, and effectively, as you can see from here, we've got the standard, we've got we model the header, and all of these fields here you'll see unsigned 4 bits, bytes, you'll find all the integers, unsigned integers, signed integers, 8 bits, obscure numbers of bits, 8, 16, 32, all those sort of bits. So effectively, that's what we get. What we can do from here, just like JAX-B, is click on a button and it deploys the code for us, and that just makes life much easier. Same with the fixed standard, the entire fixed standard, we put them in. You can see down here we've got the 0s and the 1s. These are optional, so 0 or 1, we can have 0 to n, we can have 1 to n, we can have 1 which is mandatory, etc., etc. And all of this now is sitting in a model that we can now start to work with. So what we can now do is, remember I said before, we need to abstract the layer at the bottom, which is designed for the best network efficiency, slightly up to another layer to where a business user can now start to say, I want to get this field or I want to get that field. They don't want to get the bits. They want to get the numbers. They want to get the stuff that relates to the business. So for example, if we want to find whether a field is there or not, let's say whether a phone has a particular feature or not, that might be communicated in the protocol. So we just want to find out whether it's there. I don't want to programmatically inside my Spring expression or inside my rules engine have to start testing a bit from a 32-bit field. What I want to do is to get a Java Boolean that says, is this set? So what I've now done is I can generate the code that abstracts the binary level or the network level and provide a more user-friendly level. So again, I can test bits here. If, for example, I have a field which bits 4 through 6 represent a number, in this case 4, 5, 6, there's 3 bits in there, that gives me 7 or 8 different, 7 different options, no, 8, 7. 8, thank you. Yes, 8, you're right. That's the mojitos not working for me. So it gives me 8 different numbers. It's very easy for any programmer to put those in. You simply mask it and shift it, and it gives me the number. But that's not what I want. I don't want to provide this for a programmer to do it. I want to provide it for a business user to be able to sort based on this number between either 1 and 8 or 0 and 7, depending on how it's interpreted. What I want is get version ID. And I don't want to have to do the bit testing. So this is what we now get from this abstraction level. So we now go from this binary. Believe me, I've sat and stared at this sort of thing. This is an actual message. I've changed number of values in there because obviously you'll get the slides afterwards and somebody will go, whoa, hang on a sec, I'll type in these numbers, and he's contravened our NDA or something and put someone's actual part of a phone call up there. So these are changed, just to save you the bother of going to find out what it is. We go through this. So I've got a little DOS box open there, or not DOS, it's a little command shell written up there. As you can see, I hex dumped this, and I'm sitting there going through these. And these values here, where we see, for example, BF, that could be 3 or 4 different values in there. And so what I'm trying to do is abstract this out and create a nice level for a business user to be able to access. And this is what I want to get into a Spring-like spell expression where I can basically root something. Now imagine if I can now parse them really quickly, and if I can root them, I can now start to reduce the number of messages I'm getting in certain parts, because I want to say, give me all the messages of this particular type in that one, give me all the messages of this one, this is a smartphone, this is a what's the opposite of a smartphone, an idiot phone or something. Put these into different realms and therefore reduce the amount of processing I need to do further down the line. This is my goal. So is the job done? Unfortunately, no. When we roll this out, we can get about 20,000 a second, because what's happening is it's doing the equivalent of a DOM, a document object model. So it's parsing the entire message, that hex that you saw, and it's creating an object model which looks like the graphical display that you saw, which has a header and it has multiple repeating elements, etc. And we're taking all the information out all of the time, every time. 20,000 a second for a single core isn't bad. Laptop's got 8, well, hyper-threaded 4 cores, but we'll typically get somewhere between 4 and 6 times that out. So we may well see 80 to 120,000 messages a second, which isn't bad. That's one laptop. Put it into a few servers, we could potentially do 500,000 a second. It's just not going to fly, though. So what we needed to do was to improve the performance of this. So that's what we spent a number of months doing. And interesting thing is, because we've modeled the message now, and we're using a code generator, if you change the way the code generator works, it works for all the messages you've got. You don't need to re-engineer each message one after the other. It's a code generator, and that makes it really neat. If you find a little way of saving a bit of time, you put it into the code generator, and it solves the problem for every single message you've got. So we can do it for the telcos, and all of a sudden it fixes all of the financial services messages. So we started to use this wonderful thing, which I'm sure many of you have played with, called a byte buffer. There's a little example there which I wrote yesterday, just to give you a sort of an example of what it does. It's not particularly sort of super clever. It's relatively low level. What it does is basically wrap a byte array. It does provide us with some interesting things. Now, if you were programming in C, you wouldn't take the buffer, copy it each time, and pass it as you move from function to function. You'd pass a pointer to it. You'd maybe make it read-only or const in C. That's what the byte buffer does for us. So when we get the message in as a byte, or it's sort of an array of bytes, as you remember the hex that we saw, we can wrap it with a byte buffer, as you see here, with the byte buffer.wrap, and we can move it around from our methods internally without actually having to copy it or create new instances of it. Interestingly, as you can see here, we've got things like get int, get short, get char, just get, which gets a byte. And we can do that using a built-in position. So if we do get, the position increments each time, which makes it easy to trawl through the byte buffer. Or we can also do get and then pass in, as you can see. Where have we got an example? Yes, so right in the middle here, we've got a get short 2. And that actually provides the position. So sometimes we want to get bits that are halfway through the message without having to go all the way through. You can also set the position. You can also get the position back. It's pretty useful, though. So imagine now, I've just taken the word there, John, and it represents hex 466F686E, as you can see from the comment, for those of you that's got good eyesight. What we can now do is we can extract the information out of that as and when we need it, but not all the time. So imagine now, if I want to get the third character out of that, I don't need to get the J, the O, the H, and the N. I can just get the third character as and when I need it. And that's exactly what we're doing. So we've now got a whole pile of getters. We basically initialize the object with the byte buffer, and all of the getters simply calculate where the field is that they want to get out on the fly. So if we want to get out bits 4, 5, and 6 out of a 32-bit integer, or 32 bits, we can get the byte, or in this case, get the long. We can mask it, do an and then we can shift it in the getter. And that means we get the information on the fly. It's just basically lazy parsing. So it's exactly what we're doing. If you're sorting messages and you're routing messages, you're not going to be sorting and routing on the entire content of the message. You're going to be sorting and routing these messages based on 1, 2, 3, or 4 fields. This is an assumption we've made, and it's generally held true for the vast majority of situations we've got. So it's the equivalent of a SACS parser. We simply go in, get the bit of information we need. So we've now gone from performance, in the examples we've got, just to give this particular one, we can go from 20,000 a second, while we do the DOM equivalent, to very comfortably over 1 million a second. Interestingly, the customers have provided us with these, I'd say, big files. They're big enough that you can't email them. There are sort of 100, 200 megabytes, which don't particularly compress very well, as you might imagine. this 200 megabytes holds 500,000 messages, for example. We can pass through that in literally a couple of hundred milliseconds. So it's that fast. So we're really now striving to get enough data. So that's basically solved the problem on the parsing, and that's the solution that we've got on that side. Now, as you might imagine, we pass the problem down. So as you improve the performance, the problem gets passed down as we move down the line. The problem now comes on the routing. So put this into Spring, for example, and what Spring is doing, if we take this expression at the bottom here, so where the payload.duration, so we're looking for the duration of a call. Interestingly, let me explain how the duration works. You know what a duration of a call is, obviously, but because it's binary, they don't use floating points. Yes, there's an IEEE standard, but they don't use that for this thing. They store it in ints. So we have a start time as an integer, which is the standard Unix epoch. Then we have start time microseconds as an integer. So to actually get the start time, we have to add the integer divided by a million to the other integer. And that's the same with the end time, and obviously to get the duration, we have to actually do 4 getters, which gets the end time, the other end time, the start time, subtract the 2, and that gets the duration. Now imagine if we provided that at this level. This is the business user who's going to get rather confused as to why do I have to add all of these different things up, do the division, et cetera, et cetera. What we can now provide is a get duration, and this demonstrates how we've abstracted how the message level has sort of abstracted away up to a business level. So if you take this sort of syntax here, what happens is that this now gets put into, it's compiled, generated into reflection. And so what happens now, you get the payload duration LT is less than 0.1. It generates something very similar to this. And this, if you're interested, you can just cut and paste this bit of code here. You sit it in a loop, sit it in 1 million times, you will not parse that in less than a second. It's really, really slow. And when I use the word slow here, you'll see I put it into quotes. I'm not saying Java's slow, I'm not saying reflection's slow, but for what we need to process 1 million a second, it's way, way, way too slow. This was in the realms of 700 nanoseconds. 700 nanoseconds will give us 1.4 million a second, but that's just one. If you put a second criteria in there, that's 1,400 nanoseconds. We're now down to only 700,000 a second. Add to that the time to do the parsing, and we're really starting to get down to the crunch. Remembering now that if we don't process these and we get a peak, that peak is going to cause us a lot of problems. So we need to keep this, the message parsing and the filtering, at the sort of performance level in the sort of million a second. So we need to keep comfortably below a microsecond. So what we're looking to do is to shave this 700 nanoseconds considerably down. So interestingly, I remember from some time ago, inside the Java tools, there used to be the compiler. And you could create a bit of code and you could basically launch the compiler. And then I discovered that there's actually a compiler built into Java 1.6 now. This is really cool. What you can now do is you can actually write code on the fly and compile it inside your VM and then load the code up. So next couple of slides will give you an example of how to do that. What happens now is this code is loaded up. The JIT compiler can also come in and optimize it. So rather than interpreting these things, we can actually load it up as if it's native code and have this run inside the engine that we're working in. And when I tried this out, it took me a little bit of Googling, a little bit of trying around, a little bit of sort of messing around. Sort of half an hour later, I'd got it working. The performance was stunning, really, really stunning. So just to give you an example of how I did it, and then I'll talk about what Andy Clement has been working on. Unfortunately, timing is really bad for the talk. He's talking in another talk at this very moment. I was hoping he'd be able to stand next to me and go into a lot more detail on the Spring side of things. But let me give you an example of how I just tried this out to get it working. So I created an interface, which I called an accessor, and that has a single method, a double accessor. Now I could do a double accessor, an int accessor, a byte accessor, a string accessor, etc. Remembering that I'm trying to avoid object creation here wherever possible. So basic types are much, much more efficient. Rather than strings, I'd use byte arrays, etc. Now, if I create a small class, I've called this class temp, as you can see, which implements the accessor. If I generate this class on the fly, now what I'm trying to do is go back to the previous slide. I'm trying to have a user create something like duration. Today it might be duration, another one might be start time, end time, longitude, latitude. I want to be able to make this query dynamic. It's for anyone to choose any one of these getters on the fly. So I now automatically, as you would with a typical spell expression, I can now take duration, I can capitalize it, put the getter in front of it. I could do some testing. I could actually make sure whether that exists. Don't forget, it's going to take a little bit of time to create this and compile it, but that's a one-off. So as soon as I submit my query, in goes half a second. I can double check that the syntax works. I can double check that I can use reflection. I can actually test whether the method exists. I create my class and I return the variable. So I now do in this particular case, the object dot get duration. I can now compile this. So this is how basically I did it. Again, found this on Google. Took a little bit of sort of messing around. Some of the examples didn't work, and there's all the usual little bits and pieces. And again, you'll get the slides afterwards, and if you wanted, I can just copy and paste the bits for you. So you use the tool provider class, which is a static method which gets me the Java compiler. And I just, in this particular case, used a string writer, and I can just basically write the code of the class. Now, this is the class that you would be writing dynamically, and this is the one that you would be taking the method from the query and using get duration, get longitude, get latitude, etc., and I can do all the comparisons in there. And then I basically create a file, and what I did again, copying someone else's work, as is all the best programmers plagiarize other people's stuff. Basically, changed, modified a file. What was it in here? A file object. And basically it's an in-memory file object. So I can now compile this. This is basically how the compiler works. You provide all the standard parameters that you're used to. So the -d is where I'm going to chuck it in for the destination, because that now goes into my class path, and I can now load this up. It has this diagnostics. That's basically all the stuff that it prints out. So you remember when you, in the old days, before you had Maven and Ant and bits and pieces, you used to write, do you remember that? You'd write Java C and compile stuff on the command line. Yeah, that was a while ago. You remember it used to come up with a little sort of circumflex underneath to say you've got an error here or can't understand the syntax. This is where all the information comes from. So it says what's the error, where does it start, what's the, this is all the information. So this is the information that when you're using Eclipse, for those that like a lot of painful development, or IntelliJ for those that actually like to get on with the development. When you're using this, this is where all of the sort of information comes up to tell you what's working and not working. And that basically, that's all you do. Compile it. You hope it compiles. I did find let me go back to this class again. You really need to create this and try it out on its own first, and then put the wrapper around it to create it. Because if you put the wrong package or you forget to import something, it's a little bit hard to debug in memory, if you like. So create it first is my advice, and then put the wrappers around it. And basically to run this is really nice and simple. You just do a class.forename, load it up, and you've got your accessor, and you can now do the get double. Now the first two lines naturally you'd put outside of your loop because you only need to do it once. So you'd have the compilation, you'd load the class up, and you can now use it. This is native. There's no difference. I can run it 100 million times and it's the same speed as if I had used the native get duration method. So this is what we're talking to Adrian Collier about this, again, because we're working in detail with with sort of on common clients with this stuff, and he immediately got in contact with Andy, and Andy's now put a proposal in to do basically this compilation on the fly with the spell queries inside Spring integration, etc. So bringing this into Spring, these are literally slides that Andy wrote, and I put 3 or 4 slides in there to give you a little bit of background of what can now go back into Spring. So there is, as you might imagine, some sort of optimization in there. If you're doing reflection, there are certain things that cost time and can be time consuming, but those are cached. And this is the sort of thing that happens in Spring expressions at the moment. And I've put, again, slow in sort of in quotes, because this isn't slow. Everyone here, you're all, I'm assuming, using Spring, Spring integration, Spring batch, etc. It's more than adequate for the vast majority of stuff. But again, we're trying to get down to the sort of millions per second. We need to get down into the sub-microsecond for this sort of stuff. This is way too slow for us. So what they're looking at now is basically, if the expression is used a lot, it can go off, pre-compile it, and run as native code. So again, last few weeks we've exchanged quite a lot of code. We've actually taken customer code. We've now got customer code running through with this, and these are some sort of ideas of what we're getting at in terms of performance. Basically, accessing a property inside a method has gone down from 100, and this is again 5 million operations, gone down from 931 milliseconds down to 29 milliseconds. So a good, 30-fold in performance increase on that. Looking at the invocation of a method, this is the example that I showed you before. We go down from to 2 seconds, literally, to run 5 million operations down to less than 1/10 of a second. So in this particular case, 20-fold, is that 20? Yeah, 20-fold increase in performance on this. This is significant. And this, again, is without, this is just trying stuff out as a little test. So there's more optimizations. We're basically using Java P, decompiling the code and looking at the code to see how this is optimized. So interestingly, remember now we're generating the code behind this, and we're also now generating the queries that Spring is running. So this is getting pretty fast as we're flowing through this. Drawbacks, there are plenty of drawbacks. If you're really going to be careful when you're initializing variables and doing things, as you'll notice from most well-written code, there's lots of asserts, checks, all sorts of bits and pieces that go in to make sure that you're not setting values that go beyond buffers and buffer overfills. And this, unfortunately, is the sort of drawbacks that we have. But there's also the drawbacks that you have with super high performance. If you want to do this, you don't have time to check for all these buffer overflows every time. So you've got to be a little bit sort of inventive and careful on this. Another issue we have are exceptions. If you're working in a very multi-threaded environment, if you start throwing exceptions when something goes wrong, it really creates a lot of havoc. There's a lot of deep stacks in here, and as you basically throw exceptions, this really causes a lot of problems. So we're really having to be careful about the code that we write in this sort of environment. You don't get the checking that you wanted. You've got to be very, very careful about buffer overflows, because for security reasons, and obviously it's just going to kill whatever you've got, and you need to be careful on the exceptions as well. But what we do get out of this is dynamic rules that an end user can now specify to say, do this, do that, do the other, etc., and we can get sub-microsecond performance. We can push this sort of stuff through at incredible rates, and we're now starting to see that. So, messages coming in, parsing them, routing them, filtering them, and we're now right into the core. This is where the database, and I use the word database very, very carefully here. Database could be an SQL database. It could be simply a flat file. It could be a NoSQL, the usual, the Mongos, the Redis, all the usual Cassandras and bits and pieces, or it could be an in-memory database. In this particular case, in two cases, both production code and prospects and other stuff that we're putting into production, in this particular case, is Gemfire. Gemfire is basically taking all these messages, and we need to be really careful about, we can't just throw 100,000 messages a second into Gemfire and expect all the processing to be done there. This is why we need to process it on the outside to reduce the amount of information that we're sending in, and then we put the interesting and the important information into Gemfire, and we get far more efficient usage of it. Again, remember the volumes. Even though it's 500 bytes that are going in there, if you put a few minutes or a few hours worth of data, you're going to need unbelievably large amounts of memory to hold all this in memory. One of the advantages we're getting from here is now the message comes in, we're parsing it, but we're not actually creating lots of objects, so it stays as a byte buffer. and we can extract the information out of it. We can route based on the information that we've got out of this byte buffer. Interestingly now, we can pass it along to Gemfire, and Gemfire can handle it in exactly the same format. So we're not actually creating or transforming the object from the same format that it literally comes in off NIO or off the socket or whatever it is, directly into Gemfire. Also, the serialization works in exactly the same way. To serialize it, we don't need to go through serialization, and deserialization is horribly slow. It uses reflection. So Gemfire overrides this, and you can use get data and set data, and all it does is write out the byte buffer. But it's the same byte buffer. So we're going all the way down beautifully efficiently from directly out of the socket straight into Gemfire through the routing, and it's super, super fast. So massive advantage. So triage, I use the word triage here, it's basically the message routing, filtering, sorting, straight into Gemfire. So we can now put a small section of the data, because we can say this isn't important data, this is data we don't need to store, or this is data we don't need the content of. What we may need, for example, is aggregates of that data. We may need the minimums, the maximums, the averages. We can calculate that on the fly now. We can calculate this through compiled code, and we can put that data into Gemfire, and we're saving the amount of memory that we're using. So we're putting a fraction of the information into Gemfire and using it far more efficiently. We've got less garbage collection, we've got less stuff to manage, and a lot more information that we can process through. So we're getting huge advantages from this process by handling all of the triage, if you like, out at the boundaries of the application. So is this coming back to CEP? We're talking about distributed rules and CEP. Hopefully now you can understand how we've distributed these rules. We've taken the rules from the message level. We've now applied quite a lot of business semantics into the rules. We can present these as spell queries. We can present these a little bit further up into when I say sort of engine, we can now provide rules that someone can actually use a language like Scala. Again, we can compile it and we can run these directly on the messages. Now we've got less data, but more efficient and more effective data inside Gemfire. We can now start applying these rules directly into Gemfire on all of the objects that we got in the cache. All of the things that I've seen from CEP engines to date, there were 2 recent acquisitions for very large vendors in the CEP space. Everything that I've seen in those, we can potentially do in what we've got in the solution here. I'm not saying it's easy if you want to do, if this moving average changes over this, and this one is, we have this in stock and we want to sell this, et cetera, et cetera. That's the complex part. Complex rules will always be complex. Whether you program them in a DSL or whether you program in Java, it's still going to be complex. That's the nature of it. But we have a working solution that will now give us a completely distributed and extremely powerful rules engine that will very, very easily handle complex events at over 1 million a second. So that was about an hour. So a couple of the technologies we're using, I'm pretty much wrapped up on what I'm talking about here. The technologies we're using on this, naturally we're sort of working with and looking at Spring XD. There's a lot of Spring integration here. We get a lot of the performance out of Spring Batch on this. Rabbit, again, is used a lot to move these messages around. This is a distributed environment, so Rabbit is providing the connectivity between the various different nodes we've got. And from my side, the C24 is basically what's doing the parsing and creating these byte buffer objects that we're now pushing into Spring. And for those that have seen me talk here before, we've done quite a lot of integration in the past, over the past few years, pushing the C24 into providing sort of Spring for nasty things like Swift, Fix, and ISO 8583, and all these sort of weird formats. And now this is moving into the telco range and Fix. There's some details on there if you need to contact me. We've obviously got loads of time. There's another half an hour or so. So for anyone that wants to, obviously I'll open it up for questions, and anyone who wants to go out and get some early food, please do so. So thank you very much. Question here.
Interesting discussion. You mentioned rabbit in queue. I was actually expecting you to say
Yeah, when you go into a client, you don't dictate what they've got, and these are large banks and telcos, so they tend to say we've got this, 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 and this, and we want to do that, and naturally we choose whatever they've got. So 29 West, yeah, you'll see 29 West in there. You'll find TIBCO, you'll find MQ series, you find all of these sort of bits. So we go in as neutral as we can be, and when we're working with Pivotal, we go in and the Pivotal guys, some of them I can see here, will go in and sell the full Pivotal stack. But if we've got a carte blanche or a clean slate to go in and provide an architecture, and quite often we're talking about a big chunk of the solution, we get to choose whatever we want to put in there. If they've got, for example, 29 West in there, which I think was sold recently as well, then we'll use that. But it's Rabbit fits in far better in this particular scenario, and it's an AMQP implementation, which is quite a step up in terms of advantages over some of the proprietary formats. And Rabbit MQ is on the same realms of performance. Then you've got things like LMAX, Disruptor, and all these sort of things as well. There's a lot of different choices. But we tend to go on whatever the client's preference is. Yep.
Do you look at any other open source rules engines or CEP engines like rules?
Yeah, I think so. The question was, sorry, I'll try and repeat the questions for the recording. So did we look at any open source engines? And I think you probably saw on the slide I mentioned D-rules or Drools. Yeah, and we have used it. I found it awkward, but it's most of there are quite a lot of different rules engines out there, and sort of some of them fit the bill, some of them don't. Some of them are designed for different purposes, and in financial services we have what's called sort of long transactions, not the transactions that you or I sort of start transaction, do something, commit, that happens in fractions of a second. The long transaction will take place over several days or several hours, where you start a trade, you communicate with the corresponding bank, they send back the confirmation, you do the matching, you send over something else, and that happens over a long period of time. Now the rules engines in this case often use memory to hold state, and of course over a long period of time, when you've got these transactions coming in at 20,000 a second and you want to hold those for several hours, it creates issues and problems. So you find yourself adapting to the specifics of how the rules engine works. So yes, we have used them. But I think what we're trying to do here was using the technology that we've got to actually create a more scalable distributed rules engine. D-rules is limited to a single machine. It's good for what it does, but it's limited in terms of scalability on that front.
If they have an environment that they really care about the flexibility, they have a lot of business users, they change the rule every day. So in that case, you still have to use a rule engine, or?
So question about, obviously as the rules are changing literally every day, and do we use a rules engine, or do we need a rules engine for that? I think that was the question you're asking. You saw me we talked about multiple levels of rules, so sort of at the message level as we go all the way sort of up from the semantics, the syntax, the routing, up to the matching, the rules engines, and right the way up to the top. The more facilities you provide for someone to use, the more they'll use it. So the answer is yes. If you provide them with something which is programmatically bound, then and you tell them it's going to cost a programmer to make the change, they'll use it less. If you provide something which is now inside an XML config file, they'll use it slightly more. If you present them with a GUI that they can change that on the fly, they'll use it even more, and they'll use it more and more and more. So yes, the answer is you have to provide them with ultimately with a graphical front end or some sort of environment where they can browse through the history of the rules they've just done. You've also got the concept of checking. Sometimes you might, I'll use the case, it was actually an interesting case where we did use D-rules where we were looking for fraud, and we were providing this for credit card transactions with some colleagues that sitting in the back there where we were. What you want to do is set up the rules to say if this situation occurs, we want to throw out this as a potential fraud. The problem is if you make a mistake in the rule and you have false positives, you've got 10,000 messages a second coming in. You get 10,000 messages a second saying this is fraud. If you've hooked that up to your email service, you've got a rather efficient denial of service on your email account. So with the rules engines, with the graphical user interface, what you need to do is to set up scenarios where you can say, pick this rule and now test it against the data over the last hour, for example, to make sure we don't get false positives. If that works, then submit the rule, et cetera, and then you have things that need to be checked by other people because it's going into production, and then you have this delicate situation where you're allowing people to make changes to potentially production systems, which causes some issues in some cases as well. So yes, the more you provide in terms of graphical interfaces, the more people will use it, and that's just, that's why we wanted to create something very, very flexible here. It gives you plenty of potential, is very scalable, and the next thing there is to build graphical interfaces on top of it. There was a question at the front here. He asked the same question. Okay, great minds think alike. Any more questions? Yeah, sorry.
Have you done any benchmarking on the performance between your approach and other rules engine complex?
So have we done any benchmarks with rules engines? No, it's really hard to do. I mean, we have a massive problem getting hold of data to start with. Clients don't give you data, and you have to turn up on site and get all sorts of, pass through all sorts of background checks and things before they'll even let you close to the data. And then the scenarios are so complex by definition. Complex rules engines are complex for that reason, and what we're trying to provide is a framework using largely open source that will allow us to be very, very flexible with the rules, but we're not trying to compete with a rules engine. A rules engine, there are some superb ones out there that do the job beautifully well, and they're sort of built and run. You plug them in and they work out of the box. This doesn't work out of the box. It's, we've got demos that work out of the box, but it's a framework. It's a pile of tools that allow you to do that. So no. So we haven't compared them, but I know for a fact, for doing some of the simplistic stuff with D rules and things, yes, we can outperform that by a significant margin, an order of magnitude at least. Sorry, wow, good stuff. That was the first hand I saw. So. So what do we use to generate heavy loads? And to be quite honest, most of the benchmarks that we're doing, we have client data. As I say, we get these like 200 megabyte files, which under most circumstances would be quite adequate. It would take you a few seconds to process through. We now bung these things in, and it says we run 10 loops through it, or 100 loops of this 100 megabyte file, and it says done, average time 136 milliseconds. Which creates issues. So what we do with that is we take the same thing, we'll run it through 100 times, for example. We'll create multiple machines, and it's one of the issues that I can't see the chap from Spring that's doing this, but it's we're trying to create sort of compute farms where we'll get 100 different machines that will basically pick up this stuff. We'll randomize some of it, because now, interestingly, remember that we've now got an object that represents the data that we've got. So this is the Java binding. What we can do is read the data, we can make small changes to that, randomize it, anonymize it, etc., and we can fire that out. And that's one of the things we do. With the telco data, it's a little bit difficult because you're getting data which is it's got geographic geolocation in it as well. And so what you're trying to do is to watch people moving up a freeway, for example, or looking for certain, when they're sitting on a public transport, or you see areas where people use it. If they're stuck in traffic, they text more. If they're driving on a freeway, they text hopefully less. And it's really, really hard to generate that sort of information because it's human stuff. So it gets really, really difficult. So it is a problem. So things we do use, we take existing data, we fire that through hundreds of times. We'll take the existing data, we'll use the bound Java objects out of the C24 products, and we'll basically put little randomizing bits in there, and we'll throw that through, and we'll generate sort of tank files out of that. We're talking gigabytes of this sort of stuff. Any more questions? Yeah.
If you had a rule to fire if the average speed, if this new message drops below the average speed, where do you
So the question is so when you say average speed, you mean average speed on a telco sort of?
Yeah, let's say you had 1,000 events previously.
So, sorry, I'll repeat the question once I've understood it. When you say speed, I was referring to people driving up freeways from telco thing. Were you talking about that speed, or are you talking about speed as in performance of the number of messages we got coming through?
The traffic speed.
Traffic speed. So it's a scenario which we haven't got to yet, but so the question was, how would we calculate average speed, for example? We haven't got there yet because we're not put this into production running this sort of stuff. But given the data we've got, it's the sort of thing, and we know the client has asked for this sort of thing, and we know that's the sort of thing they want to do. I saw a really interesting talk by someone who worked at Nokia, was demonstrating the searches using Hadoop or MapReduce to basically look at the searches and look at where people are when they do the searches. And it was quite interesting watching people driving around the ring road around London looking for the search words. And he did an example of IKEA. Now IKEA, there's an IKEA store, a couple of them sort of as you have them here as well, around the ring road, the M25 around London. And of course they look for IKEA when they've driven past it. Because they know they should be getting off. They see the big IKEA sign and they think, shit, am I gonna, how do I get off the freeway? How do I get back to it? So of course they're texting, looking for how to get a map to look back to how to get to it. So thinking about that, how would we calculate the speeds? The speeds would, on a GPS you get the speed, it's part of the data. I've not seen it in the telco data we've got, so you'll have long and lat. So to calculate the speed, it's going to be a simple, yes, there's a great circle calculation. For short distances, you wouldn't do that. You'd use Pythagoras. So you'd work out, position 1, position 2, time 1, time 2. Therefore, you got the speed. That doesn't take into account, however, stopping, starting, changing direction, all the other bits. So there's some sort of averaging. So that again, just like I've mentioned, you've got duration. Duration is calculated from the end time plus the end time in milliseconds minus the start time. You would create another, shall we say, business function called getSpeed, and getSpeed would do the calculation of distance over time. That would provide you with the speed. In terms of how would you keep averages of that, well then you'd keep, as I mentioned before, you'd keep an aggregate of that in something like Gemfire, where you'd keep an ongoing average. And again, that would be something that you would compile because you would need to do it at performance. So you'd take out the speed, you'd create an average of that, you put it into Gemfire, you'd then distribute the average speed to say, if anybody passes out of the seconds standard deviation of the average speed, then book them for speeding or whatever it may be. That's thinking out loud. So.
Is there a rule authoring language
That's an interesting question. Is there a rule authoring language? There are a number of rule languages, and it's something which is. We've had a lot of discussions about this. What language do we use to define these rules? These are interesting discussions which we've had for several hours and have normally been matured in the bar. That's the way we work in London afterwards. The sort of concept we came up with, at the level that most of us here are working in, we'd prefer to work in Java or Scala, for example. That would be the rules that we'd use. So we'd be defining these things in our programming languages. You get to the business user. The business user is sitting there with an Excel spreadsheet. So we thought, yes, we could create a DSL for these. I mean, the spell is a DSL. It's not ideally suited for rules languages. What we came up with was probably something as similar to an Excel spreadsheet. So if we were to emulate all of the functionality of an Excel spreadsheet, the business user would be able to understand that very easily. So for the moment, again, this is work in progress on this particular side. We can do whatever we need to do, but you're right, as the question someone was asking earlier, do these change dynamically? Yes, the answer is they change very, very dynamically. So would we provide a GUI for that? Yes, we would. We'd provide the GUI, we'd provide something, the lower level would be Java, the next layer up on that would be Scala, which allow us to abstract some of the brackets and bits and pieces. And then the next layer up from that would probably be providing the functionality of something like Excel. Sad that it may be, but that's what business users use. But they'd be able to understand the syntax of AVG for average, min, max, and various other bits. And then, of course, you could add to those to do different sorts of averages and Bollinger curves and all sorts of weirdities. So no, we've not particularly taken on a standard rule language. Any more questions? Another one there?
I just wondering if you can clarify on how the message is identified. So when the raw data comes in, somehow we need to mark the start of the message and the end of the message. And then we pass on the way down to the gem-cac. Then how did they move back and forth? Because this seems very hard. It cannot move too far back or forward, right? So there has to have a kind of like a unit where within this unit the process takes the authority and compare the conversion and jump through or the one bit and into something throughout. But you cannot just go so far. You cannot from this message to 100 bytes away from it.
Yeah, let me extract a question out of that. I think the question was relating to, so the relationship between the messages you're thinking?
Right, the data comes in that certain format. How we interpret? I think the key here is we don't want to copy the data. We want to check data coming in or speed. But that's how we overcome the data is streaming from the back. So all of a sudden, how we now do it is one unit from independent.
Okay, so there's, rather than go backwards and forwards in trying to extract, I think there were two possible parts of the question, and excuse me for not understanding it entirely. So question was about how do we split this up into, how do we split the messages up, and then how do we provide the context across the messages over some sort of time. Again, going down to the Y level, the messages come in and they've got in the header of the message, it basically, again, it's binary, it says how long the message is. So at that level, it's relatively easy. We've got the first word or the first 4 bytes in there just say how long the message is. So if we've got a big chunk of data that's coming in on a stream, we can basically read the first 4 bytes. It'll tell us how big it is, and we go to the end of that. It's a bit like a sort of the way the Pascal string used to be. We just know how big it is. So that's how we chop it up at the Y level, those sort of things. So we get a large chunk of data in, read the first 4 bytes, tells us the length, chop it off. That's a section, we can move that on. And we go on to the next one, read the first 4 bytes, and off we go. So that's how we chunk it up at the Y level. When you move up the stack to the business level, then there's more context that comes into it. So if you've got they don't use phone numbers when they're tracking things. They use this, another thing. It's not the IMEI thing. It's another thing called an IMSI or something like that basically tracks one particular, phone or conversation. Naturally, now you've got to provide some context to say, here's the part of a message from somebody using their phone, and then you get another 20,000 messages from something else, and then here's the next part of the same thing. So there is quite a lot of, you're not tracking every single phone all of the time. If you wanted to track one phone, then you've got a blacklist, you've got whitelists, and then you would be providing state for those. So you would be filtering out certain conversations, should we say. Conversations could be binary or voice, or data or voice. You would be doing those on the fly. The rest would be averaged out. So you're not necessarily providing the context for all of the messages all of the time, because that would result in quite a lot of computational work. Again, one of the other advantages is if we can sort, for example, already on the outside the data with the voice, we can put the data into one Gemfire region, we can put the voice into another Gemfire region, and then we could then split down the data into further subcategories, and we can then start to track those individual conversations. And we might have a special one for blacklists, a special one for whitelists, et cetera, et cetera. So we basically would distribute out the processing. Does that answer your question? Great, thanks.
What do you guys do in such a distributed processing, handling failures like hardware failures?
What do we do with, how do we handle failures? Tend to basically just assume that failures will happen, but because you're in a very largely distributed environment, it's something that if the data, certainly for financial services, is far more critical because you can't afford to lose parts of your data. To a certain extent, in the pre-trade environment where you've got price feeds coming in, it doesn't really matter if you miss one or you miss a few because it's replaced fractions of a second later by something else. In the post-trade, you've got financial transaction that's taken place, and there's no way you can lose that. So that's when you start to have resiliency, and then you start to have two sets of everything that go through. And typically we use compensational transactions rather than individual transactions. So we put 100,000 in, we make sure we get 100,000 out. If we don't, then there's a problem. We can process it through again. So it's idempotent. You can bung it through any number of times without changing the results at the end. We don't use the classic transactions, the 2-3 phase commits, etc., because that just kills performance. It's just not possible. So it's basically compensational transactions. And again, it's down to the business level as to whether you can afford to lose data. In some cases you can. Sometimes you could say, the business user will say, you'll go to them, business user is the person that's paying the bills, so they're very important people. And I've had this conversation numerous times, and you're trying to plan to build something. You say, so how important is this? What level do you need? And they say, oh, I want 6 nines, please. It's got to be absolutely there. No, 6 nines, that's 1 in a million, and I do 1 million, every day. No, I need 9 nines of performance or reliability out of this. And you come back with a bill of how much that's going to cost, and it's, no, okay, I'll 3 nines will be fine, thanks. And it's just a matter of what will happen if you lose this. The financial consequences of losing it, which is has a probability attached to it, is far less than the cost of insuring against it. So it's a business decision at the end of the day. And you have to build that in, because every extra 9 that you add in terms of reliability costs more than 10 times more. And in many cases, if you explain what happens, once every 3 years, you may get a failure that may take you an hour to recover. Can you afford that? Yeah. Well, it's cheaper to assume that will happen and design against it than it is to actually ensure that it doesn't happen, which even if you ensure that it doesn't happen, it will happen. The more hardware you put in, the more likely it is to fail. Flying a twin-engine plane is a lot more difficult than flying a single-engine plane, and because you've got 2 engines there and they're twice as likely to go wrong. Another question?
I imagine that some of those variables that you would use for processing the messages through rules come from more historical data. Just wondering.
Yeah, that's an interesting question, and it's so some of the data comes from historical. Some of the data that we're using for the queries comes from historical. Yes, that's actually part of the architecture that we were asked to design in. So it comes in multiple layers. So we have variables that are calculated on the fly. So these are sort of, let's say, moving averages, which are calculated in real time. Then you have data which, so as you go through the sort of an archival layer, you have data which is maybe pre-calculated in the morning or changes during the day. So you have another layer of variables which are, in financial services, would be the opening price or the closing price from yesterday or something like that. And then you have another set of data which is perhaps the result of a map-reduce process that was done over the last week. And then you have another set of data, which is really, historic data. So we have multiple layers of this, and that data is something that's calculated overnight, calculated on separate processes, and then is loaded back up. And we use distributed cache. I've used the word lightly, distributed cache. We use a sort of distributed environment like Gemfire to distribute these numbers across all of the processing nodes. So yes, there are lots of different layers of historical data. There's sort of real-time aggregate data, there's daily aggregate data, there's calculated aggregate data from Hadoop style map-reduce processes, and then there's the sort of stuff much further down. And all of that has to be provided back as part of the scenarios. And these are the sort of things that, again, if you're writing a graphical user interface on top of this, you would provide these in sort of drop-down lists of, do I compare this with the opening price? Do I compare this with the average from the last month? Do I compare this with the current average, et cetera, et cetera. So all these will be variables that we would have to hand.
As those variables change, I guess in the interim, you won't get tomorrow, whatever. There's no kind of real-time pushes.
Well, again, it depends where you draw the line as to there's some variables that will change constantly, in which case they need to be provided. We go for we don't need consistency across all the nodes. And if you're comparing an average and an average is not updated quick enough, generally, again, this is another business decision. Do you need consistency across everything? Unlikely, because it's, if you're doing that sort of thing, it's not that critical. And consistency now means you've got a distributed environments and you end up with the usual issues that you have in that sort of environment and providing consistency. So some things will change in sort of pseudo real time. Others will change, will be fixed for the day. But from a formula point of view, you don't need to account for that. It's how you optimize the performance behind as to whether the variables are sort of say volatile or whether they're fixed.
So in the case of fraud detection, let's say I have historic data, I live in New York, all of a sudden I get an event I discharge in Santa Clara. Would that logic sit inside like a precompiled
So the question is, if you have credit card transactions, you're looking for fraud detection. Obviously, you live in New York, you use your card in New York, and something goes through in Santa Clara. It's the sort of typical case, as you'll probably notice from your credit card transactions. There's nothing to stop you, obviously, making a transaction in New York and then doing something in Santa Clara, particularly if it's an e-commerce type of transaction. That's going to happen naturally. But if you physically turn up and sign your card in both places, less than it takes a plane to travel between them, then that's definitely a potential fraud case. Those are sorts of scenarios where you're maintaining some sort of state, which is a moving window of for each of the transactions. Again, a couple of colleagues I was working with, sitting at the two guys, stick your hands up, John. And John, that's John and John. I'm John as well. So nice, nothing to. These guys were working with me in a company called Revolution Money, where we were doing fraud detection. We were using D-rules and various other bits at the time. So you may want to sort of go into more detail on sort of how we were doing some of that. But it's a sort of situation where you've got to every time you get a transaction through, you've got to go back through some historic data. And then also you've got things like offers as well, where you've got to say, when this person spends $1,000 in this particular store over a period of time, then you've got to again go back through the transactions to see how many times. So it's again, for each transaction that happens, you've got to go back through some of the historic data. I doubt very much we would do that sort of thing at a million a second, so it's not the realms that we would get in this. However, if you had that data coming in, don't forget we're now sorting out, we're doing triage where we're taking a lot of the messages out. What we're getting is what's left, and we're now down to a few thousand per second in terms of transactions. We now have that sort of capability where you get a transaction in at maybe 5,000 a second. We've now got more than enough time to trawl back through the last 6 months, I think was what we kept, 6 months of data to see, is this transaction, A, is it fraud? And B, do they get a reward for having used a certain thing a number of times? We have we have the capability of doing that, not at a million a second though. But fortunately, the numbers that come through, even at Visa, where I just spent the last 3 years working as chief architect on the v.me, we don't have that sort of volume going through. We had about 180, was it 180,000 a second or something like that, sort of volumes. So. And again, those volumes peak, you get something like half of the year's entire volume goes through in the US in the sort of Thanksgiving week. But they peak at that sort of number, but it's not the same sort of peaks you'd get at 1 hour before midnight on a telco where everyone's sending texts to say, Happy New Year. Any more questions? One more? You again. So was the question asking where we would store that sort of information?
Right, is that the data independent of the technology computer, and we have to synchronously with everything?
Again, in the credit card transactions, the volume of data is significantly less than what we're looking at in the sort of telco realms. In the telco realms, it's the entire country's worth of messages, where you're getting, even just from one phone, dozens of messages a second. In the credit card transactions, you're getting a small section of those. You know, Visa was the worst case scenario because they process such a massive volume of the world's data. So in the cases we were dealing with, we were processing a very small section of those. So we had more than enough time and more than enough memory to store 6 months worth of data. I think it was about 1 terabyte of in-memory data that we eventually built out of that. It's lunchtime, guys, so I'm going to suggest we call it a day. Thank you very much.